Hey everyone. So, as of the last video finishing, we sort of have the model laid out, and we've got the basic vocabulary kind of developed that we need in order to talk about these things, talk about the Turing machine model effectively, and we sort of built up the basic vocabulary and the basic definitions. Now what we need to do is kind of make a slow, unfortunately kind of boring march towards a very, very essential thing, which is we need to build a universal Turing machine. That's kind of the base, you could say, of the whole theory. Is we really need to build one of these, and we really need to be convinced that they exist, and we really need to be convinced, and we really just need to be more familiar with the Turing machine model. We have the model kind of laid out now. We've got the vocabulary to talk about the model. What we need to do now is really sort of develop the model a little bit, get familiar with it, get comfortable with it. And as we do that, we're going to be sort of doing all of that in the sense of building towards a universal Turing machine. And the way I see it, it's going to be a three-step process. So step one is we're going to need to understand subroutines. That's what we're going to do this video. I'm going to try to show you an example of like using one Turing machine within the context of building some bigger, more complicated Turing machine. So we need to be convinced that we can do that without much thought, so that I can talk about it without just describing everything explicitly. The second thing we need to do is prove some of what I'm going to call like robustness facts. What I mean by that is I've even said a lot of these out loud without justifying them. I've said to you before, it doesn't matter how big the alphabet is, as long as there's at least two symbols. It doesn't matter whether or not the Turing machine extends infinitely to the left and the right. It could only go in one. It doesn't matter how many tape strings it has. I've said these things before, but I want to convince you of them. And some of these proofs are extremely tedious, so I'm not sure how much of a proof how detailed of a proof I'm going to show you guys. But we're definitely going to talk through all four of these and talk about how in concept at the very least you would go from one of these types of models to another, and we're also going to need to discuss kind of the time and complexity loss, efficiency loss in time and space in doing that, and more particularly show that that doesn't matter either. That's really the important thing is we really need to make sure like it's obvious enough, I think, to most people that the number of tape strings probably doesn't matter, right? Most people could believe that. The issue is, do we lose a lot of time in going from five tape strings to just one? And the answer is no, but that requires a little bit of convincing. So I want to convince you guys of that stuff. And then once we've done that, then we'll be in a really good position to build a universal Turing machine. Once we've got these robustness facts, the rest of the theory development will be a lot less anal kind of feeling because we'll be able to just kind of we'll be able to kind of use whatever kind of model feels convenient for the moment in order to do what we need to do when proving other things. So these robustness facts are pretty boring to even talk through, let alone prove rigorously. But once you have them, the theory becomes very loose to the point where some people kind of even scoff at it and be like, this isn't rigorous at all. But it is. It's just these robustness facts are very powerful. So let's get started on that. So as an introduction to the subroutine stuff, I've actually kind of uh, we've got I wrote down a Turing machine here. I gave you the table of it. Let's zoom in a little bit. So here's a Turing machine. Uh, so we've got the basic alphabet, the start symbol, uh, space, and 0 and 1. I've got 5 states here and a transition function, which is given by this table that I just printed out. This table, by the way, is from my notes, and my notes are linked in the description of this video, and they will be linked in the description of every video following this one. So I recommend you check that out. Um, and so I want to do an exercise with you guys while we figure out I've given you the Turing machine, but it's pretty hard to just look at this and know what it's going to do. You kind of just have to run it and to see. And so what I want to do is an exercise with you guys where we see exactly what this does. And then we're going to think about embedding it as what its action as a subroutine. So let's just draw. So I've recommended that we run it on this input 0, 1, 0. So let's just do that. So the initial tape configuration is going to look like this. And it's just spaces going left, or going right, I mean. So of course we start with our cursor on the triangle, and we start in the state S. S is my starting state, by the way. And then H is the halting state. And you can see that just from looking at the table. So this is the initial configuration, and now we can sort of think about the simulation. We can just think about what this Turing machine is going to do just by kind of doing it ourselves. So we're in state S. We're looking at a triangle, so we look that up, and what seems to happen is we stay in the state S, we leave the triangle alone, and we move right. That's the first step. So now we're pointing at the 0 and still in state S, so we look that up. If you're in state S, looking at the symbol 0, then it looks like we stay in state S, we leave the 0 alone, and we move right. Now we're pointed at a 1, and it looks like we leave the 1 alone again, and move right again. And then we're going to be in state, we're going to be pointing at the 0 in state S, and we've already done that. It tells us to move right again. And now we're going to be on the fourth step, I think, pointing at a blank in state S, and it looks like when we're pointing at a blank in state S, we go into this new state Q, we leave the blank alone, and we move the cursor left. So far it seems like all the algorithm's really done, all the Turing machine's really done, is move all the way to the right until we found a blank. And remember, by default, we assume that inputs don't involve blanks. So putting a blank here means that it seems like we're searching for the end of the input. It seems like that's what we've done so far. So now we finally found the end of the input. We're pointing at it, and we're in this new state Q. It seems like to indicate that we found it. And we're pointing at a 0. And what that says to do now is erase. It looks like what we're gonna do is erase the 0. But then we're going to go into the state Q0, which, if you remember the algorithm that I laid out for, um, uh, what was it actually? Uh, Palindrome detection. We kind of had this. We had a state Q0 then too, and that existed to remember that we had a 0. And it looks like that's just going to be kind of the same thing going on here. It looks like we're erasing a 0, but we're remembering that we had it here with this state Q0. I'm going to erase this. We put a blank here in its place. We'll move to the right, it looks like. And now we're in state Q0. And so now we're in state Q0, looking at a 0. I should be moving my cursor with my actual cursor. You can't actually see my mouse moving around if I'm moving around on the pad. I have to use my mouse. So we're in state Q0, looking at a 0. And it looks like, according to the table, when that happens, we go into state S. Oh, sorry, we're in state Q0 looking at a blank, in which case we replace the blank with a 0. It seems like what we do is we replace the blank with what we remembered was right before it. Um, and then we move left and we go into state S. Okay, now we're in state S looking at a blank, which, just like before, moves us left. Moves us left and into the state we had before, Q. And now we're in state Q now, looking at a 1, in which case it looks like we go into state Q1 and erase it just like before and move right. So it looks like just like before, we're erasing the thing we had, going into a state that remembers it, and we're going to be looking at a blank now in state Q1, which says to erase the blank, put a 1 in the blank, I suppose, going back into state S and move left. So let's do that. Oops. And I think you can see what's going to happen again, just like before. We're at a blank in state S, so that means we move left to go into state Q. And now we're in state Q looking at a 0, and just like before, that means we're going to erase that, replace it with a blank, and then move the cursor to the right in state Q0. Now we're looking at a blank in state Q0, which means that we replace the blank with a 0. We move left and we go into state S. If we're looking at a blank in state S, we move left again and we go into state Q, just like before. And then finally, we're in state Q looking at a start symbol, and it looks like that is the situation in which we halt. Looks like we also halt if we exit state Q0. We halt, leave it alone, move right. And now the computation has halted. So what did we do? What did this computation accomplish? Well, we took the 0, 1, 0 input and we outputted. Looks like we're not deciding anything, but remember, if we just have a halting state, then the interpretation is that the resulting string is the output. And so it looks like the output string is just 0, 1, 0, but with a blank in front. So what does this machine M sub S do? Well, it seems like it takes the string that we input and moves it to the right by one cell. It seems like it's a space creating machine. It is a space maker. It moves stuff over. It creates space for us. So as a subroutine, as a Turing machine on as its own machine, this thing is worthless. Nobody wants this. But in the context of another program, I think hopefully people can see how useful this potentially is. And indeed, I didn't pick this for no reason. We're going to use this a bunch of times, improving our robustness facts, and even in making a universal Turing machine. This is actually going to be a very important subroutine to have convinced you exists. Um, so that's what this machine does, and so this is something that we want to think about talking about using. Like, I don't look at this big table. I don't want to write this out again. I just want to talk about using a machine. I just want to be able to argue that I can always do this, that I can always take everything to the right of my cursor and jam it over to make space. I want to be able to just do that on the fly. So how could we do that? How could we embed this as a subroutine in the context of some larger Turing machine? That's what I want to ask. Well, let's think about that. Well, and by thinking about that, what I want to do first is I want to think about kind of exactly what it is we're asking for. So what exactly do we want? Well, what we want is this. We have this situation where we have tape. We made this too long. We have some stuff, and then we're pointed at some symbol sigma. We're in some state, I'll call it P, and then there's some more stuff on the tape. And then of course there's an ending to that, and there's blinks going forward after that. So this is my situation, and let's say that when I'm looking at the state sigma and I'm in state P, when I'm looking at the symbol sigma in state P, then what I want to do is I want to produce space in front of me. So I want to basically have the same stuff going up to sigma, and then I want a space, and then I want the stuff that I had before moved over. So this is what I want. Oh, and I guess I should say, I'll call this state P1. I want to leave the sigma alone, and I want to be like right here in state P2. So this is exactly what I want. I want a subroutine that will go from this to this, that will produce a blank in front of the symbol that I'm looking at, with everything else that's important jammed to the right. Now, how can we accomplish that? Um, so let's see. Let's think about it. Well, I'm going to assume that none of the state symbols that I used in M sub S, none of these guys. I'm going to assume that none of these state symbols have been used yet, and also obviously that we have the same alphabet, sort of. I'm going to add a couple symbols in. So assume that none of any of these symbols, S, Q, Q0, Q1, and H have been used yet as states. That's just going to make things simpler. If they have, then I got to use new symbols, and that'll complicate things. But that's that. Now, the subroutine up here, uh, it uses two assumptions. It uses the assumption that there's a start symbol to the left to give an indication on when to stop, and it also uses the assumption that there's a blank symbol on the right to know when to like search for the end of the string. I'll deal with that. I want to talk about the last point that I made, the blank at the end. I want to talk about that uh, maybe after we've already discussed the subroutine and overlooked something. But in terms of the start triangle, we don't have a triangle. Instead, what we have is a sigma, right? I want everything to the right of the sigma to be a blank. And so what I'm going to do is I'm going to introduce a new symbol, a special symbol, sigma with like a line under it. It's a marked sigma to take the place of triangle. So it's going to basically take the place. It's going to be something. Triangle is never going to be used anywhere, right? X is a string of zeros and ones, um, and so it's never going to be used. And that's how we're allowed to use it as like the left marker. So and there could be sigmas in this string right here. So I can't use this as a triangle unless I like replace it with like a special marked version of itself. That's what I'm going to do. And indeed, what I'm going to do is I'm going to replace the place symbol with sigma bar everywhere in the transition function of m sub s, the subroutine. So that's what we're going to do. In fact, I'm just going to write it in just to make sure that people understand exactly what I mean by that. I mean, up here, there's a triangle here. Get rid of it. Replace it with sigma bar. Whoops, sigma bar. Right? There's a triangle here. Get rid of it. Replace it with sigma bar. There's a triangle here. Get rid of it. Replace it with sigma bar. Everywhere that there's a triangle, I'm going to just replace it with sigma bar. Okay? Um, and now what that's going to do is that's going to, and so obviously I need to start out by replacing sigma with sigma bar. So to start, have delta of sigma p1 be equal to sigma bar uh, uh, s 0. So I'm not going to move. So what's that going to do? So I've got my stuff, and then I've got sigma, p1, got stuff, and blanks. And so what that's going to produce is it's going to produce stuff, sigma bar. It's not going to move the cursor. I'm going to be in state S. So that's the tape. That's what the tape is going to look like at that point. And then you can see I'm in state S. If I just leave delta alone, if I just keep this exact table. Now, this is a partial definition of delta. There's going to be other stuff going on in my definition of delta for this big machine M. But in terms of just making delta as like a pile of instructions like this, I can just leave everything else alone. I can just leave everything else alone. Um, and so what I can kind of say is like define delta as above for all you know for all states uh, S, Q0, Q1, Q, and H. It kind of looks like a B, but it's a 1, right? Just leave it alone. And what's that going to do? Let's just think about it. Well, that's going to, um, so that's just, this is coming back around here. It's going to produce stuff. It's going to give me a sigma bar. It's going to have a blank here with a cursor. it's going to be in state H. And then I'm going to have stuff and then my blanks. And so that's almost what I want. Remember, if we look above, what I really want is this tape string up here. So the only differences now are that I'm in some state H when I want to be in state P2, and my sigma bar should be gone. It should be sigma again. So finally, define delta of, I guess, blank. It'll be guaranteed to be a blank, right? H to equal, uh, obviously we want to move left, but that's the last argument. Uh, Blank again, we want to leave the blank alone. That's what we wanted in the first place. Um, we want to move into state, um, I don't know, H prime. I'll just make a new one up, and left. And then delta of sigma H prime, sigma bar, excuse me, equals sigma P2 and 1. And so what that's going to do is it's going to produce this, whoops, it's going to produce the exact thing I want. It's going to produce stuff, sigma, blank. I pointed at it. I'm in state P2. I've got my stuff, and then I've got a blank, and nothing but blanks after that. Done. So that was very explicit, and I wanted to make it very explicit just to prove to you how there's a little thinking to do, but it's not hard. And it's, in fact, it's so straightforward that it's not something that we want to waste a lot of time with. I want to convince you that you can do this all the time, and I'm convincing you that you can do this with arguably the most important example. This subroutine is something we're going to need to use a lot, especially early on. Um, but I just wanted to kind of demonstrate the idea of using old simple Turing machines in the context of larger, more complicated Turing machines. Now, I mentioned there's one complication, and that complication is basically that if I was abusing the fact up here that the input doesn't have blanks in it in order to not having blanks in the input means that I can search right in order to find a blank in order to find the end of the string. But if the string has blanks in it, then that's going to create problems in terms of the algorithm. I'm not going to move everything to the right. I'm only going to move the stuff that's before the first blank to the right. So how do I deal with that? Well, there's a lot of ways to deal with that. Maybe the simplest way to deal with that would be to, just like we added a special sigma bar symbol, add instead like a special like blank bar symbol. And then at the beginning of the computation, basically like move to the right until you find the first blank, and then replace that blank immediately, like before the computation starts at all, let alone the subroutine, just at the very beginning, find the end of the string, replace it with a blank. And then whenever you need to make extra room to the right of your string in the computation, then you run this subroutine, um, but searching for a blank, but searching for like the special blank, and then that way you can kind of keep track of where the end of the string is, and that would add a lot of computation. That would mean I have to write down many more paragraphs to justify this, but it wouldn't be hard. It would just be tedious, and that's really the point that I want to make is that this is in general, not something that I want to, these are not the kinds of details that I want to be doing when I'm making these videos. I only want to walk a tightrope in which I do enough of them to convince you that I'm not skipping anything of importance. And that's going to vary for different people, but, the best I can do is, I think, just exactly how much I think is necessary. And what I think is necessary is to show people how to implement subroutines like this kind of in principle, and then leave the rest to just hand waving. Uh, so here's the kind of takeaway principle, which is that given we have a previously defined machine which produces a specific effect, we can, without extra justification, use this machine as a subroutine in the creation of larger programs. And that's really what I wanted to do for the most part with this video. I'll write down one little lemma that's kind of a restatement of this principle. Um, I'll call it, oops, oh my God. So here's a related lemma that I want to write down to end the video with. This is something that's kind of a more rigorous version of it. It involves using Turing machines. It involves composing Turing machines together, basically. So let M1 and M2 be Turing machines. Um, by the way, a lemma is like a stepping stone proof. I think that's exactly actually what the word means. It's like I think lemma in like Greek like is like the stone that you. It's like when people throw stones at the. Actually, I think it's like stepping stone. I think it's literally like stones that you use to make paths. I could be wrong about that, but basically a lemma is like a mini baby theorem. It's like a fact that you're proving to get to a bigger fact. It's like it doesn't deserve to be called something. It's basically saying it's a small fact that I have to write down to get to something more important. That's what a lemma is. Um, so then there exists a Turing machine M such that for all x, for all inputs x, um, m of x is equal to m2 of m1 of x, or m1 or of m2. It doesn't really matter. But the bottom line is that I can easily, if I have two Turing machines, then I can without any proof consideration, I can sort of run m1 of x as a subroutine and then use that result as the input to m2 and then run m2 and then get the kind of composition of the two. So basically, any two functions computed by Turing machines can be composed with another Turing machine without a second thought. Um, the only thing I have to say is where m2 of m1 of x is defined to equal that arrow symbol whenever m1 of x equals input. I had to say that because we've already defined what this means. It means that the machine doesn't halt, but we haven't considered what it means for the input to not halt, and so I have to kind of add this special caveat. But the bottom line is that I can compose functions. I can pose. I can. Alternatively, the composition of two Turing computable functions is itself Turing computable. And I think that's going to do it for our discussion about subroutines. So in the next video, we will begin to prove those robustness facts. We'll prove that staying still is unnecessary. We'll also prove that the number of symbols is unnecessary. I am not looking forward to justifying the second one of those. It's very annoying. But I will see you then.